Waves in strings, question 2. A guitar string of length 0.65 meters has a fundamental frequency of 262 Hz, which is note C. A part 1, draw a diagram of the string vibrating at this frequency. Well, the fundamental frequency is the lowest frequency, so we have half a complete wave between the points. So we'd need a diagram something like this. For part 2, draw a diagram of the string vibrating at 4 times the fundamental frequency, and mark the nodes with a capital N. Well, if we have 4 times the frequency, we'll have a quarter of the wavelength, so we can now fit 2 complete waves in between the gaps. It's always useful to mark faintly some of the points, for instance marking the peaks and the crossing points, before you actually put in the lines to do a diagram like this neatly. Don't forget to mark in the nodes. Well, the nodes are where there is no displacement, so that is at these points. These points in between the nodes are called the antinodes. Part B. The string is now shortened by pressing it on a fret on the neck of the guitar. The string now vibrates with a fundamental frequency of 294 Hz, which is note D. Calculate the new length of the string. Well, it's useful here to gather what information we have. So we know that the first frequency was 262 Hz, the second frequency 294 Hz. The first length was 0.65 of a meter, and we want to find the second length. The datasheet gives us the relationship fundamental frequency equals 1 over 2L root T over mu, where T is the tension in the string and mu the mass per unit length of the string. Now, tension and mass per unit length of string are constants, and so we could rearrange, bring the L up here, and find that F times L is equal to just constants, so FL will be a constant. Taking that one step further, we can say that F1L1, the first frequency and length, multiplied together will be equal to the second frequency and length multiplied together. Rearranging for L2 will equal F1L1 over F2. Putting in the numbers, this gives us a second length of 0.58 meters.